We built the brain, placed the memory, and drew the pipeline. On paper, this design is perfect, but in digital design engineering, there is one truth. A design is nothing more than a claim until it has been tested. The market does not send you the packet you expected, like clean, ordered, well-formed datasets. It sends you malformed headers. It drowns you in sudden traffic surges. It creates price gaps. It generates edge cases. These are the situations that digital design engineers did not think of, did not simulate, did not test, and these situations kill you, silently, within nanoseconds. Welcome to the verification stage. This is Axiom Tech and I am Epoch. In this video, our ghost trader will come face to face with reality. The test bench is a hostile environment. You wrap your design in an artificial circle of chaos that simulates the real world. At the center of this simulation sits one module. That module is the device under test, the DOT. In our case, the ghost trader's entire RTL architecture contained within a single DOT module. On the left is the stimulus generator. It impersonates the exchange. It produces packets in real fixed protocol format. Normal packets, corrupted packets, packets arriving too fast, packets arriving too late. In short, every possible packet scenario you can conceive. On the right is the scoreboard. It captures every signal leaving the DOT. It compares it against the expected behavior. If they match, your system is working. But if they do not match, your design has failed, and you go back to the beginning for another round of revisions. Any failure you experience happens here, in simulation, not in the real market. Think of it this way. To know whether a building is truly resilient, you do not build it and wait. Engineers ignite controlled fires, simulate earthquakes, apply flood tests. Sensors inside the building record the responses. The test bench is exactly that, the controlled chaos environment that tests the ghost before it drowns in the real thing. Hardware simulation has traditionally been written in System Verilog or VHDL. But cocotb offers a different approach. Hardware can be tested with Python. The simulator, Vivado Simulator or Model Sim, runs the RTL underneath. cocotb reads, writes, and controls signals from above through Python coroutines. Await rising edge. Wait for the rising edge of the clock. .valid.value 1. Drive t-valid high. .valid dated value 0x4142434445. Inject the data. These lines are not abstract. They are the real signal values of your circuit inside the simulator. When you write Python, Silicon speaks. Think of it this way. A conductor does not play the instruments. They tell the musicians what to play and listen to the result. cocotb is exactly that. You write the instruction in Python. The simulator orchestra plays that instruction every clock cycle, and you, as the conductor, decide whether the result is correct. Passing a normal test is easy. If the design works on normal input, that is only the beginning. The real question is this: what does the ghost do when it sees the unexpected? First edge case, truncated header. The packet arrives half-formed. Talid goes high, but the tall signal never arrives. The pipeline waits. It enters an infinite loop. This is a deadlock. In the real market, this means a pause lasting milliseconds. For an HFT system, milliseconds means death. Second edge case, back-to-back packets. The second packet arrives while the first is still being processed. The BRAM write port is busy. A collision occurs. Risk of data loss. Imagine this scenario. A car enters the Formula One pit, but the previous car has not left yet. The mechanics were not designed to service two cars simultaneously. The system collapses. The race is over. The collision in our pipeline is the same thing. Two realities cannot be processed at the same time if you were not prepared for it. Every edge case exposes a blind spot in the design. Every blind spot demands a fix. Every fix demands a resimulation. This cycle, test, failure, fix, retest, is the essence of verification. Saying the simulation passed is not enough. You need to see what happened. The waveform viewer is the microscope of time. It shows the value of every signal at every nanosecond. When a problem arises, and it will, you go back, look at that exact nanosecond, and understand what went wrong. Talid went high. Treddy stayed low. The handshake did not occur. Data was lost at that nanosecond. We see it in the waveform, 1/1247 nanoseconds, exactly there. This precision, this surgical accuracy in fault detection, is what simulation offers. Finding this fault in real hardware takes days. In simulation, seconds. This is like a watchmaker who dismantles a complex watch and lays every gear on the table. Why is the watch running 3 seconds late? The watchmaker examines each gear one by one until the worn part is found. The waveform viewer is exactly that. Every gear of your design, every nanosecond, right in front of your eyes. Functional verification passed. But there is one more exam. Timing closure. Your design may be functionally correct, but it may not be running at the target clock frequency. Worse, negative slack is showing a negative value. This means some signal paths cannot complete within a single clock cycle. In a 100-meter race, the target time is 9 double seconds, but the athlete crosses the finish line at 10:20 seconds. The race is over, and the athlete has lost. Timing closure is the same thing. Every signal path must complete within the defined clock period. If it cannot, the design does not work. You could lower the frequency to solve the problem, but we do not want that, because frequency is speed. If frequency drops, speed drops. We do not want that to happen. The solution: adding a pipeline register. With a pipeline register, we split a long combinational path in two. Each half of the combinational path then completes in a separate clock cycle. The delay is halved. We reach our target without lowering the frequency. Latency increases by 1 cycle, but when the pipeline is full, that cost becomes invisible. WNS positive, TNS 0. Timing met. That is all. We have satisfied the timing constraints. The final exam is not synthetic test data. It is real historical market data. March 2020, the period when markets lived through one of the most chaotic days in history. Tens of thousands of ticks per second, prices in free fall, packet density at maximum. The Ghost is processing this data at real-time speed. 10,847 packets, 0 errors, 187 nanoseconds average latency. The Ghost entered chaos and emerged from it through deterministic physics. Tested, verified, confirmed. Theory became reality. But this is not the end of the series. A verified design is still not silicon. In the next encounter, synthesis, place and route, and the Ghost being etched onto real physical silicon, implementation begins. This is Axiom Tech, and I am Epoch. I will see you in reality.